we have a two-part theorem. First a lemma, and then the theorem itself, which we're going to prove to see the properties of our estimators for the estimable functions. We start with the lemma, and we need to do two things. We need to show that there is a unique linear unbiased estimator, and if we have another unbiased estimator, then our unique estimator is the projection onto V. So let's start with this. So we assume that we have an estimable function. We know then, according to the definition, that we can find an A, which is such that the expected value of this linear combination of the y's is equal to psi. And now we split this up. We write A star for the projection of A onto V, and then we subtract and have B star as the perpendicular part. And then, of course, since B star is perpendicular to V, it's also perpendicular to the rows of the X matrix. So the expected value of B star Y is 0. Now, it's perpendicular to the columns of X because it's in V and because it's outside V, perpendicular to V. Now, therefore, we have found an unbiased estimator, which is in V. Now, suppose then that you have another one. Then we know that the expected value of the difference is 0 because they have the same expected value. And we know that A star minus alpha is perpendicular to the columns of X times the beta. Now, this has to hold for all beta, so it has to be simply perpendicular to the columns of X itself. And that means that it's in the perpendicular space to V. But, you know, we assume to begin with that both A star and alpha are in V, and that means that they're both in V and D perp, and the only thing that's both in a space and perpendicular to it is the zero element itself, which means that A is equal to alpha, so it's unique. And we're therefore done with the lemma. Now, this is really, really neat. And the lemma itself is well worth looking at carefully. In other words, for any estimable function, we can find an estimator, which is such that it is in V, so it's a linear combination of the column vectors of the X matrix. So only stuff which is generated from the X matrix is estimable. Now, the Gauss Markov theorem itself then is a little bit more elaborate. Any estimable function has a unique unbiased linear estimate, which has minimum variance in the class of all unbiased estimates, and this is unique. And it can be written as the corresponding linear combination of beta hat, where beta hat is any least squares estimator. And you'll notice what this says is that whatever least squares estimators you take, you get the same value of C prime beta hat. And let's start glancing through this. First of all, we use the lemma and take any other unbiased linear estimator. Then we know that A star is the projection of the vector A onto V. And we know that, since it's a projection, A is equal to A star plus the difference, and the difference is in V perp. So the norm of A squared is the sum of these two according to the Pythagoras theorem. And therefore we can look at the variance of A prime Y, which now is just as we derived a long time ago, A prime sigma Y times A, sigma Y is sigma squared times the identity matrix. So this is just the norm of A squared times sigma squared. Now take the norm of A squared, split it into these two components, and this second part here has to be non-negative. This first part is simply the variance of A star Y. So we've shown that the variance of A prime Y is greater than or equal to the variance of A star prime, should say prime Y here. So A star Y is the best linear unbiased estimator, if you like. Now, let's now take any least squares estimate and see what happens with that. happens with that? It is a least squares estimate. So x beta hat, according to definition, is a projection of y onto v. And y minus x beta hat, since x beta hat is a projection, is in v perp. And that, since a star is in v, this inner product here is 0, or a star prime times the y minus x beta hat is 0. And therefore, a star y is equal to a star x beta hat. Okay. So we have an a star y, which is equal to a star x times beta hat. So in other words, there is a c here yelling at us. So this particular c tilde, if you like, times beta hat gives us the estimator. Now, since this is estimable, we know that c prime beta hat is equal to e a star prime y, which is equal to this quantity on the right-hand side. This holds for every beta, and we therefore realize that c prime has to be equal to a star x. For these to be equal to for all betas, the vectors must be the same. So in other words, we have the same value of a star prime y as we would get from c prime beta hat for any beta hat, any least squares estimator that we want.